Okay, in this video we'll see one method to find inverse of a matrix, and that method is using elementary transformation, specifically elementary row transformations. So let's say I have a matrix here, which is a 3 by 3 matrix. It has entries -1, 4, -2, 0, 2, 2, 0, -3, -2. So yeah, it's a square matrix, so we can expect its inverse to exist, but the condition that it should satisfy to have an inverse is that its determinant has to be non-zero. So the condition that we need to check first of all is that determinant of A has to be non-zero. So let's find its determinant. The determinant of this matrix is nothing but this it's a number, and this is the way to find its determinant. This is kind of a refresher to find the determinant of a 3 by 3 matrix. It is nothing but you start with the first entry -1, and you multiply it with the determinant of the submatrix. So I multiply it with the determinant of this submatrix: 2, 2, -3, -2. Then I need to subtract the next entry multiplied by its submatrix. So I have 0, 2, 0, -2, 0, 2, 0, -2, and then I'll add the next entry 3 times the determinant of its submatrix, and in fact that's not a 3, that's -2. Sorry, -2 times its submatrix, which is 0, 2, 0, -3. So 0, 2, 0, -3. And yeah, let's just find this out. This is -1 times this determinant is 2 times -2, that's -4. Let me just write this whole thing: -4. Now I need to subtract this multiplication. So this multiplication is 2 times -3 is -6, and subtracting a -6 is as good as adding a +6. So I can write it like this. Next I have -4 times. Now this determinant is 0 times -2, that's 0, minus 0 times 2, that's 0. It's just 0 minus 0, which will result to give you a 0. And lastly I have a -2 times again a 0 times -3 is 0, and 0 times 2 is 0. So this again gives you 0. So I can really forget about these two terms. 0 minus 0 will give you 0, the product will give you 0. 0 minus 0 will give you 0, the product is 0. So I just have to worry about this. This is 6 minus 4, which is 2, being multiplied by -1, which is -2. And the most important fact here is that this is not equal to 0. So this is not equal to 0. So I can be sure that A inverse exists. A inverse exists. So that, yeah, there is surety. Now we can use transformations to find its inverse. The fact that its inverse exists says that if you have your matrix A being multiplied by its inverse, you get your identity matrix back, right? And in particular, in this example, you'll get a 3 by 3 identity matrix. So if I were to just plug the matrix A here, I would get this, right? I would get a -1, 4, -2, 0, 2, 2, 0, -3, -2. And let's say I don't know what A inverse is. That's my ultimate goal, to find this A inverse. But I know what a 3 by 3 identity matrix looks like. It's actually just ones along the diagonals and zeros everywhere else. So now this is the crux of this process to find the inverse by elementary transformations. What you do is you do some transformations on both sides of this equality, and we know from our previous theory that if you do it on both sides, the equality is still maintained. So if somehow I could transform this matrix into identity matrix, you will realize that what remains over here will be the inverse matrix. We'll do that, and we'll see how that turns out to be the case. So yeah. To convert this to an identity matrix, my very first goal is to make the first entry 1, right? And then I can use only row transformations for this. So it's already -1. So if I were to multiply the first row with a -1, so that would give me a +1 here, right? And it would of course change the other entries, but let's not worry about it. So the elementary transformation that I need to do first is -1 times R1. So if the first transformation is -1 times R1, and I need to do this on both sides. So So if I'm doing this over here, let me do this over here. So if I were to just let me get this in range. So if I write it over here, this will be my left hand side matrix. I'm multiplying it with a negative one. The first row is multiplied by negative one, so this entry becomes 1. This 4 becomes a negative 4. This negative 2 becomes a 2, and everything else remains the same because I'm not changing anything for the other rows. It's 0, 2, 2, and 0, minus 3, minus 2. And I still have an A inverse over here. I haven't tampered it at all. And if I do the same thing on the right hand side, I am simply multiplying the first row with negative 1. So if this is 1, 0, 0, it will turn out to be a negative 1, 0, 0. I'm just multiplying the whole row by minus 1. And of course, everything else remains the same. 0, 1, 0, 0, 0, 1. Now the next logical step would be to make the other entries in this column to be 0. But here if you see properly that the other entries are already 0. So we will need not worry about it. We can go to the next column. For the next column, I need a 1 in the second row, right? So right now it's 2. So if I were to make it a 1, I will have to multiply the whole row by a half. So I'll have to do this transformation, a half into row 2. That is what will make this entry to be equal to 1. So if I were to do this, it wouldn't change the other rows at all. So the first row and the third row will remain the same. It will remain 1 minus 4 2 and 0 minus 3 minus 2. What will change is the second row. It will become half. So half of 0 is 0, half of 2 is 1, half of 2 is again 1. So yeah, and of course I have the A inverse, and I have to do the same thing on the right hand side as well. So right now I have a 0, 1, 0. If I multiply it with a half, it will become a 0, half, 0, and everything else remains the same. Next, my goal is to make the other entries in this column equal to 0, because ultimately my goal is to transform this into identity matrix. Right? So I have got a 1 here. I have to make the other entries 0 using just elementary row transformations. So you can do that by using this 1 that you have got. So I have a minus 4 here. What if I were to add 4 to it? And that I can get that 4 by multiplying this row by 4. So what I am expecting to do is I want to change R1, and I want to basically add 4 copies of R2, so that this will become a 4 times R2 will become a 4. Mind you, I'm not changing R2. I'm just using the scalar multiple of that row. So I'm multiplying this by 4. I'm adding it to the first row, so that will nullify this. So this will become a minus 4 times minus 4 plus 4, which will give you a 0. That's my ultimate goal. So if I do this, since I'm changing R1, my R2 and R3 remain same, so I don't tamper the other rows. And yeah, I'll have to do this term by term. So if I add 1 plus 4 times 0, now 4 times 0 is just 0, so I'm not tampering this value at all. So you see why you need to get a zeros in other end, in the other parts of the column. So that's the importance. Yeah, this was the whole thing that we wanted to do. Minus 4 plus 4 times 1 is actually 0. And yeah, of course, 2 plus 1, 4 times 1 is 2 plus 4, which is 6. So this gives you 6. And of course, I have an A inverse, and I need to do the same thing on the right hand side as well. Again, I'm just changing the first row, so the second and third row remain same. And now I am doing minus 1 plus 4 times 0. That's just minus 1. 0 plus 4 times half. Now 4 times half is 2. So 0 plus 2 will give you a 2. And 0 plus 4 times 0 is just 0. So this is it. Now I also have a minus 3 here. I need to make it a 0. So again I can use the same second row. I can add 3 times this second row to this, so that this becomes a 0. So what I want to do is I need to change R3 now, and I'll change it to, I'll add 3 copies of my R2. So I'll add 3 times R2. So this will become, since I'm changing R3, my first and second row will remain same. I'll have a 1 0 6 0 1 1, and my third row is changing. Okay, okay, let me not write it over here, it's a bit not legible. Let me write it over here. So my first row is a 106, my second row is 0 1 1, and I'm changing my third row to the third row, adding 3 copies of the second row. So 0 plus 3 times 0 is just 0. Negative 3 plus 3 times 1 is negative 3 plus 3 is 0. And negative 2 plus 3 times 1. So that's negative 2 plus 3, that is 1. And of course, I have my A inverse over here. I am not tampering it at all. And on the right hand side, I'm doing the same thing. I need to change the third row. So I need to copy the first 2 rows as is. And my third row changes to adding 3 copies of R2 to it. So 0 plus 3 times 0 is just 0. Now 0 plus 3 times half is 3 halves. So I can say it is 3 by 2. And 1 plus 3 times 0 is just 1. So this is it. This is what I have on the right hand side. And let me just copy it on the new page, and we'll resume a bit later. Okay, this is just what we were left with in the previous step. So now I have got zeros in my second column and just one in the second row. So I move on to the third row. In the third column, sorry, in the third column I need a one in the third row, and I already have one. So if this was not one, I would multiply my third row with its reciprocal, so as to make it one. But fortunately, we have a one here, so we need not worry about it. And if I have a one here, I need the other two entries to be zero. So I can make this 0 by subtracting 6 copies of 1. So I am changing R1. I am changing R1 to R1 changes to I subtract 6 copies of R3. So you'll realize that the other entries, the one and 0 that we got earlier, they won't be harmed because there's already a 0 0 over here. So those entries won't be changed. This will become a 6 minus 6 times 1, which is 0, which was our ultimate goal. And the other entry, the other rows remain same, 0 0 1. On the right hand side, I'm changing the first row, so the second and third row will remain same. And I'm adding 6 copies of the third row to the first row. So if I have 6 copies of 0, it's a 0, and so I'm not adding nothing to the first entry. If I have 6 copies of 3 halves, that's 9. So if I add 9 to 2, that's 11. And finally, if I add 6 copies of 1 to 0, I'm sorry, I need to subtract 6 copies, right? So if I were to subtract 6 copies of this, 6 copies of 3 halves is 9. So if I were to subtract 9 from 2, I would get a negative 7. I'm sorry about that. This entry is negative 7. And then 6 copies of 1 is 6. So if I were to subtract 6 from this, I would get a negative 6. And this is awfully close to the identity matrix. The only difference is that this entry is not 0. So we can make it 0 by subtracting the third row from it. So what I need to do is I need to change the second row. The second row changes to second row minus the third row. So all the other rows remain the same. So this remains 1 0 0 and 0 0 1. And I'm subtracting this row from this row. So this 0 minus 0 is 0, 1 minus 0 is 1, and 1 minus 1 is 0. And yeah, you see, you get the identity matrix. So multiplied by A inverse, of course. And on the right hand side, we do the same thing. I don't change the first and the third row, so they remain intact. Minus 1, minus 7, minus 6, and 0, 3 halves, and 1. And I'm subtracting 0 from 0, so I get a 0. I'm subtracting 3 halves from 1 half. So that's negative 2 halves or negative 1. And I'm subtracting 1 from 0 to get a negative 1. And now comes the ultimate drum roll. This is the identity matrix, and we know from our properties of matrix multiplication that when you multiply identity matrix with anything, you get that anything back. So if I were to just ignore this part, this would be just A inverse, right? This is just identity matrix multiplied by something. It gives you that something back. And on the right hand side, I have this matrix. So yeah, you have got the identity matrix. So this is the identity matrix. Right? A inverse is equals to this. And just to make the final point that this is actually indeed this is the inverse matrix. Let's multiply our matrix, our original matrix with A inverse and check whether that is actually the case. We'll do that in a while. Okay, so now let's see whether the inverse that we have got is actually the inverse of this matrix. So this is my original matrix A, and this is what we got by elementary row transformations as A inverse. We hope to get the product to be equal to the identity matrix of order 3. So let's see if we get that. For the first entry, we use the first row and the first column. -1 times -1 is +1. 4 times 0 is 0, -2 times 0 is 0. So yeah, it's just +1. The next entry, -1 times -7, that's 7. I will write it here. 4 times -1 is a -4. And -2 times -3 halves is -3. And indeed, you can see that the sum is 0. Yay. The next entry is -1 times -6 is +6. 4 times -1 is -4. -2 times 1 is -2, again giving you 0. Next entry is 0 times -1 is 0. 2 times 0 is 0. And 2 times 0 again is 0, giving you 0 indeed. Second row, second column entry. So use the second row and the second column. 0 times -7 is 0. 2 times -1 is -2. And 2 times 3 halves is 3. So 3 minus 2 is 1. Yes, we are halfway through. 0 times -6 is 0. 2 times -1 is -2. 2 times +1 is +2, indeed giving you 0. 0 times -1 is 0. -3 times 0 is 0. And -2 times 0 is also 0, giving us some 0. 0 times -7 is 0. -3 times 1 is 3. And -2 times 3 halves is -3, giving you a sum of 0. Last entry, I hope to get this as 1. So 0 times -6 is 0. -3 times -1 is +3. And -2 times 1 is -2. The sum indeed comes out to be 0. And yeah, this is actually the identity matrix of order 3 by 3. And as an exercise, you can also check that if you do it the other way around, if you do A inverse times A, you also get the identity matrix back, because the inverse satisfies this property as well. If you multiply it with either of the sides, you get the identity matrix back. Take this as an exercise.